Imagine you're hiking across a smooth hill landscape. This landscape is your space. You can walk in one direction from any point. But let's forget about embedding it into a three-dimensional space. Just focus on the ground under your feet. No up or down direction. If this sounds weird, especially because there is clearly curvature involved here, you might want to watch this video on the channel, where we cover this notion of embedding in detail, link in the description. Now, suppose that at every point on the surface, there is a temperature assigned to it. The higher up you are on the hill, the hotter it gets. It's important to notice that temperature is just a real number. It doesn't have any direction associated with it. This is the concept of a scalar function, denoted as t in this case. You stand on a point and look around. At that moment, you're standing on a spot that has a temperature value, say 80 degrees Celsius. What can you measure? If a specific direction is given to you, you can take a tiny step along it. This little displacement can be measured with a vector. However, it says nothing about what's changing in the environment. It's also important to note that the vector cannot be represented this way, sticking out of the floor, since there is no external ambient space. We also can't just draw its sort of shadow on the floor, because vectors do not bend like that. The vector actually lives in a different separate space, called the tangent space. If the hill landscape is called M, which stands for manifold, then the vector v, based on the point P, lives in the tangent space TPM, which is specific for this point. Now, think about what a simple derivative does. It measures the rate of change of something, like temperature, with respect to something else, like distance, but only as you move along a straight line, usually the x-axis. For example, if you move east, the derivative might tell you how fast the temperature changes per meter walked. That's great, but it does so only in one specific direction, not in general. However, wouldn't it be nice if we could somehow combine the best of both worlds? In other words, the directionality description of vectors and the capacity of tracking rates of change of scalar fields. That's what a directional derivative does. It requires both a scalar field and a direction, and it gives you back a number. Like, you'll feel the temperature increase at a rate of 30 degrees Celsius per meter in the direction you're heading. A directional derivative is often expressed this way. It reads as, the rate at which the scalar function t changes as you move in the direction of v is given by feeding the vector v into the one-form dt. Okay, but what is a one-form? A one-form is a mathematical object that eats a vector, so a direction, and returns a real number. However, it's important to emphasize that dt on its own, with no vector attached to it, is not a real number. It's more like a mapping, or a machine, that takes in a direction and tells you how the function t is changing along it. That's a one-form. Attention, that doesn't mean that one-forms and directional derivatives are the same thing, but rather that they're very closely related. More specifically, a one-form is a generalization of a directional derivative. The directional derivative dvt is the specific result you get when you choose a scalar function t, choose a point p on the manifold, choose a direction v, and ask the question, how does t change as I move in the direction v from p? It is a number. The one-form dt, on the other hand, exists before we've chosen any direction. It lives at every point on the manifold. It takes any direction we give it, and tells you how the function is changing in that direction.
Let's see a concrete example. A scalar field t from m to the real numbers will be defined as x squared plus y squared, where m is a two-dimensional manifold, so a surface. This function gives a temperature at each point. Pick a point p equals to 1. At this point, the temperature is 5 degrees Celsius. What happens to the temperature if I move only to the x direction? Well, let's see. Therefore, as you can see, for every unit you walk east, the temperature increases by 4 degrees Celsius. What happens if you move only in the y direction? Using the very same logic, we find this. Therefore, for every unit you walk north, the temperature increases by 2 degrees Celsius. That's great. But what about moving diagonally? Let's say 45 degrees north and 45 degrees east. Now we need to define a vector v that will encode this direction. Actually, this expression makes no sense at all in this context, because we're assuming the manifold M to be abstract. In other words, possibly curved and not embedded into a higher dimensional space. So we cannot use the basis vectors I and j of calculus in order to write the vector v as a linear combination of them. Visually, we're saying that the tangent vector v cannot stick out of the manifold. It needs to live inside of its own tangent space, TPM. As a consequence, we need a new pair of basis vectors that are capable of spanning the entire tangent space at a point P, such that any tangent vector v in TPM can be described as a linear combination of them. In differential geometry, we define tangent vectors as derivations, because we don't have a global ambient space. This is a hard concept to grasp, and is usually one of the greatest sources of confusion when people are trying to learn differential forms. So pay close attention. Instead of defining a vector by its direction in space, we define it by what it does. A tangent vector tells us how a function changes at a point. And this is exactly what a derivation does. The goal is to describe it only in terms of intrinsic properties. The differential operator partial x does exactly that. It takes a function f and returns the rate of change in the x direction. Hence, the vector v is described as a linear combination of partial x and partial y, which are not only considered differential operators in this context, but also vectors themselves. More precisely, the pair partial x partial y is the basis of the tangent space TPM, and therefore the appropriate picture you should have in mind is this. So, vectors themselves are considered differential operators when dealing with abstract and curved spaces. We put a lot of effort into our videos, so we would really appreciate it if you could subscribe to the channel and give this video a like. Back to our example. We can apply the one form dt to this diagonal direction given by this vector. The coefficients square root of 2 over 2 come from the fact that the sine of 45 degrees and the cosine of 45 degrees are both square root of 2 over 2. Remember, a one form is a mapping that takes vectors and returns real numbers. Since the vector v is an operator, we can act it on the scalar function t, which is literally the definition of directional derivative. Thus, we can also write it in terms of the result of acting the one form on the vector v. So the question is, what does dt look like before acting on the vector v?
Well, what about this? It turns out that this expression for the one form dt works perfectly. If you want to see the detailed explanation for why this is true, check out the PDF link in the description, where you'll also find a very nice summary of the entire video.
Now, we use PDFs a lot in our videos. Pretty much all of them come with PDF files. But what if sometimes you want to take notes, or change something, or convert it into a different file? Well, I've got something perfect to get the job done. It's called PDF Agile. PDF Agile is an all-in-one PDF editor that works on both Windows and online, and it's full of very useful features. You can edit text, images, even rearrange entire pages. Everything is super fast, clean, and easy to use.
Some of these PDF files are over 40 pages long and take quite a bit of time to read, not to mention that it's mathematics.
You can convert files between PDF and Word, Excel, PowerPoint, and more. without messing up the layout. It's perfect for any kind of use you may need for it.
We know there are many of you from around the world, and fortunately PDF Agile even has built-in OCR that supports 22 languages. That means it can recognize text in scanned PDFs and images. So yeah, it is pretty smart. You can crop any image to your liking. No need to look around finding them. PDF Agile has them all ready for you in a list, ready to be edited. Plus, PDF Agile gives you highlighter tools, freehand drawing, text boxes, and more.
If you were able to solve a Millennium Prize problem while reading a PDF, by chance, fortunately your data is safe with password protection, redaction tools, and e-signatures, or anything else you might need to protect your files for. And the best part, they offer free online tools, no installs, and no credit card needed. You can edit, convert, and use over 20 templates for things like resumes, contracts, and posters. All of this right from your browser. Try out PDF Agile for yourself using the link below.
In order to see that this is the correct expression of the one-form dt, though, we have to assume that these terms dx partial dx and dy partial dy are 1, and at the same time that dx partial dy and the opposite of it are 0. But how come this is true? Well, we've seen that partial x partial y is the basis of the tangent space TPM for a point P in the manifold. But what about dx and dy? What do they represent? dx and dy are covectors and also one-forms. Indeed, a covector is the same as a one-form. When we refer to it as a covector, though, we're usually in the context of linear algebra. If you want to learn about it in detail, check out this video in the channel. But just to give you guys a taste of it, when you have basis vectors e1 and e2 with subscripts, no matter if they are orthogonal or not, you can find mathematical objects denoted as covectors e1 and e2 with superscripts, such that e1 subscript is perpendicular to e2 superscript and so on for the opposite, but not to their respective counterparts. So these relations are valid. And this fact can be expressed in a more compact way as this. EI subscript times EJ superscript is the Kronecker delta. So basically the identity matrix. And that's precisely what's going on here. Partial x is perpendicular to dy, and so on for the other terms, using them as basis vectors and basis covectors. These relations are valid strictly in the sense that their multiplications give us 1 or 0 accordingly. So the covectors dx and dy form a basis for a space that is dual to the tangent space TPM. This dual space is called cotangent space T star PM. This is not actually what it looks like geometrically. It's just a visual representation of the linear algebra facts that we've seen before. In differential geometry, though, dx and dy are referred to as one-forms, and therefore they act on vectors v in order to return a scalar. For dx, this scalar or number is exactly the value of the directional derivative of the function x, or f of x equals x, in the direction of the vector v. A similar result is valid for dy. So the one-forms dx and dy are a sort of filter that extracts the x and y components of a vector. When dx acts on the vector v, for example, we get the magnitude of the vector's projection onto the x-axis, and similarly for dy. Differential forms are especially useful in very abstract and curved spaces, because they don't rely on an ambient space or coordinates, or even a precise notion of distance, like a metric. Instead of describing geometric objects as like arrows in space, forms describe how scalar functions change. They act on vectors and extract quantities like rates of change, flux, and orientation.
And forms do all of it in a way that's 100% intrinsic to the space. That's why they're perfect for studying manifolds. Even if some local regions are twisted, curved, or stretched, and even if global coordinates don't exist. So to recap, the symbols partial x and partial y represent the basis vectors of the tangent space TPM at a point P on a manifold. They describe directions of motion along the x and y coordinates that are intrinsic to the manifold. Their duals, dx and dy, form a basis for the cotangent space T star PM, which consists of linear functionals, also known as one-forms, that act on tangent vectors. This dual pairing is what allows us to write and compute geometric quantities. A vector v is expressed as a linear combination of the basis vectors, and a one-form, like dt, is expressed as a linear combination of dx and dy. When we apply the one-form to a vector, the result is a scalar, so a measurable quantity, like the rate of change, which reflects how much a vector points in the directions given by the one-forms. Let's finish this topic by applying the one-form dt, with t being x squared plus y squared, to this vector v at a point p equals 2, 1. For more details, check out the PDF link below. Therefore, for every unit you walk northeast, the temperature increases by 4.2 degrees Celsius. Before moving on to two forms, let's generalize the definition of a one-form for manifolds of any finite dimension. The dimension of the tangent space TPM is the same as the dimension of the manifold. Let's say n.
The basis of the tangent space TPM is partial x1, partial x2, and so on up to n, the dimension of the manifold. Or simply, we can write partial 1, partial 2, and so on up to n. The cotangent space T star PM, so its dual, is the space of one-forms at the point P. Its dimension is also n, and its basis is dx1, dx2, and so on up to n. From the definition of dual basis, this relation must always be satisfied, just as before. Thus, what is a one-form on this abstract manifold M? A one-form, which is very often denoted as omega p, is a mapping that assigns to each point P in the manifold a linear mapping. In coordinates, any one-form can be written as this, where the coefficients ai are smooth functions on the manifold M. Awesome! We're ready to move on to two-forms. A two-form is a function that takes two vectors and returns a number. So now we go from two copies of TPM to the real numbers. But there's a caveat here. The order of the vectors matter. This property is called antisymmetry. In order to deeply understand antisymmetry, think of vectors v and w at the point P forming a small parallelogram. When a two-form omega, which can be written in coordinates as dx wedge dy, acts on those vectors, it measures the signed areas of that parallelogram. So not just how much area it spans, but which way it is oriented, positively or negatively. Swapping the input vectors flips the sign of the result, and it produces a reversal in orientation according to the convention you pick. This property is super useful because it gives us a sort of detector of local orientation on the manifold. Now you must be wondering, what is this symbol? This is called the wedge product, and it's what allows us to construct high-order differential forms, like two forms, using one-forms as building blocks. Think of it like this. Just as adding vectors give a new vector, wedging two one-forms gives us a mathematical object that knows how to handle two vectors and return a scalar. However, just as we said before, in an antisymmetric way. Since two forms measure oriented areas, guess what area the wedge product of a basis vector with itself measures? dx wedge product with dx is just 0. Let's see what happens when the two forms dx wedge dy act on the vectors v and w as the basis vectors of the tangent space TPM. The result is +1, because the orientation agrees with the order of the wedge. First dx, then dy. If you flip the order, in other words, dy wedge dx, the result is -1. Now we generalize two forms to n dimensions. This is an antisymmetric bilinear map that takes two tangent vectors at a point P and returns a number. In local coordinates x1, x2, and so on up to xn, the basis for two forms is built using wedge products of one forms. We know that there are n factorial over 2 factorial times n minus 2 factorial such basis elements in total, and general two forms looks like this. We could also think about generalizing it to m forms in n dimensions. This is a totally antisymmetric multilinear map that takes m vectors and returns a number. Each m form is written in terms of wedge products of m distinct one forms. So the basis of the space of m forms at point P is dxi1 wedged with dxi2 and so on up to im. In total, there are n factorial over m factorial times n minus m factorial such independent m forms. To recap and conclude, this is a table that summarizes everything we've seen in this video.
If you like this video, I'm sure you're going to love this one. See you guys there.